Hello everyone, welcome to my channel. In this video I have 4 very intriguing integrals to look at, and I'm inviting you to stop this video, work on these integrals, and then come back to this video and check the solutions. Our first integral is the integral of x power 7 times the square root of 1 plus x power 4 dx. Now I want to look at this expression under the squared sign. If I differentiate this, derivative of 1 is 0 because 1 is a constant. Derivative of x power 4 with respect to x, it is 4x cubed. So I have x cubed there if I differentiate the expression under the squared sign. But I have x power 7 outside, which means I need to transform this one. So this is how we do it. So taking us to page 1, let me capture the integral. Number 1, the integral of x power 7 times square root of 1 plus x power 4 dx. Now what I told you is I'm going to break the x power 7 down as follows: the integral of x power 4 times x power 3 times square root of 1 plus x power 4, and then I have dx outside there. At this stage, I'm going to combine x power 3 with dx, because when I differentiate the expression under the square sign, like I said, you get x power 3. Of course, an expression in terms of x power 3. So now I'm going to rewrite this as x power 4 times the square root of 1 plus x power 4, and then times x power 3 dx. Right. At this stage, u-substitution comes in handy. Let u, I'm going to take u power 2, u squared, because I have a square root sign there, be equal to 1 plus x power 4. So if I say differentiate on the left, the answer is going to be 2u du. Remember, on the right, derivative of 1 is 0, 1 is a constant. Derivative of x power 4 with respect to x, it has to be 4 x power 3 dx. Now notice something here, x power 3 dx, that's what I have there. So the 4 must go there. So what do? I divide both sides by 4, and what I get is 2u over 4 du is just going to be equal to x cubed dx. Simplifying this expression on the left, I'm going to get half of u du. The answer is equal to x cubed dx. Now that expression, which is that, has to be replaced by that. Under the square sign, I'm going to have u squared. And outside here, I have x power 4, which means this equation here must be solved in terms of x power 4. In other words, I have to make x power 4 subject to formula as follows. What is x power 4? Well, you can see here that it's actually u squared minus 1. So now I have to perform triple substitution, this expression, that one, and that one, as follows. So this integral is transformed as follows. The integral of, instead of x power 4, I'm going to have u to the power 2 minus 1. And then I have square root of, remember, there is your square root sign there. Square root of, what is 1 plus x power 4? U squared. And then outside, what is x cubed dx? Half u du. 1 over 2 u du. Right. Now notice that half is a constant, so I can take it out. So what I have now is, let me move this up. What I have now is 1 over 2, the integral of u squared minus 1. Notice this is actually u, square root of u squared. This cancels that, so it's u times, there you have u, and then du. Now that will be u squared, and then we expand, we distribute u squared across, and the du as well, keeping the half outside, as follows. Taking us to page 2, this expression changes to, let me move this one down. Right, so now what we are saying is that that integral changes to 1 over 2, the integral of, watch this, u squared, one step at a time. Outside I have u squared du. Distribute, we have 1 over 2, and allow me to use a big bracket outside, a square bracket. I'm going to say the integral of u squared times u squared is u to the power 4, and then I have du, and then I have minus there. the integral of u squared times minus 1, obviously it's going to be minus u squared, and then I have du, like so. Now, evaluating these two integrals, very easy. As you can see, this is 1 over 2, and this is going to be just u to the power 5 over 5, because you add 1 and then you divide by the result. Minus, again here, it's going to be u to the power 3 and divide by 3. At this stage, remember this is an indefinite integral. There are no limits of integration here, so I must say plus a constant c. Now let's distribute the half now. So this is going to be 1 over 2 times u to the power 5 over 5 minus 1 over 2 times u to the power 3 over 3 plus c. This is just 1 over 10 u to the power 5 minus 1 over 6 u to the power 3 plus c. We must go back to our original variable, which is actually x, not u. So that means we must come back here and look at this expression here. This is u squared equals this. So what is u? We'll have to take square root both sides here. Solving for u here, you will see that it's actually the square root of this. So we're now saying, therefore, this is equal to 1 over 10, open brackets, square root of 1 plus x power 4 all to the power 5 minus 1 over 6, and then we have square root of 1 plus x power 4, and then we have to say power 3 plus c. Now what is this? What is square root of something? It's actually this expression to the power half, but we have to multiply by 5. So our final solution then is going to be 1 over 10, and I'm going to write it in this form: 1 plus x power 4 all to the power 5 over 2, and then I'm going to say minus 1 over 6, and then I have 1 plus x power 4. Remember, power half times 3 is going to be 3 over 2, and then I'm going to say plus c. So this is the final solution to our first integral, right? Very intriguing and tricky questions. As you can see, this one, the next one is also just as tricky as this one. We had to trade very carefully here in order to manipulate this so that it agrees with the simple u substitution. Right, let's look at the second integral then. The second integral in this video is this one here. As you can see, we have a definite integral this time. So we're supposed to evaluate the integral from 0 up to 2 of the square root of x squared minus 4x plus 4 dx. Now, the first thing we have to look at is this expression under the square root sign. Is there something we can do about it? And looking at the expression, the answer is yes, we actually can factorize this. It actually can be easily be factorized into a square of a bracketed expression. Let's see how it looks. So basically what I'm saying is, by looking at quadratic factorization, which I have presented in a couple of videos back, if you check on my videos on algebra, you will see that our integral number 2, which is the integral from 0 up to 2 of the square root of x power 2 minus 4x plus 4 dx, simplifies to the integral from 0 up to 2 of the square root of, check this out, and I'm saying positive square root of x minus 2 all squared dx. Expand this, you'll get that expression there. Now this is where the trick is. If you take square root of this expression, when you're dealing with definite integrals, we are focusing on the positive square root. So the absolute value comes in now. So this is going to be, watch this, is going to be the integral from 0 up to 2 of the absolute value of x minus 2 dx. Because we want to make sure that the square root of this expression here is never negative, because we're talking about the positive square root. Now, this is just, if you look at the definite integral here, it's just area under the graph, this graph from 0 up to 2. So now let's look at this. We have to sketch this. What am I saying now? I'm saying we have to sketch the graph of y equals the absolute value of x minus 2 and check. So let me remind you of the concept of absolute value. We said the absolute value, this is what we say, of x is actually equal to x if x is actually positive, minus x if x is actually negative. And so what it means, we can say therefore the absolute value of x minus 2, if you agree with me, this is just going to be equal to x minus 2 if x minus 2 is positive. And what does this mean? It means x is greater than 2, don't forget that. Or minus of this expression x minus 2 if this expression x minus 2 is less than 0. And what does this mean? X is less than 2. Simplifying this part here, it gives you minus x plus 2. Now we have to plot the graph of y equals x minus 2 for x greater than 2 and y equals minus x plus 2 for x less than 2. Plotting those graphs, very simple linear graphs, you will agree with me that this is what we have. Here is our y-axis and our x-axis. The point of interest is a number 2 there. If I move this one down like this, you'll agree with me that the equation of y equals x minus 2 will have the y-intercept at minus 2 down here. X-intercept is going to be at 2, and then it goes up straight like this. But remember, for this one, we're interested in x is greater than what? Greater than 2. Here it is. Y equals that. We're interested in x greater than 2. It means our graph, the focus is that one there. That's our focus. Now let's look at the other one. The other one is this, y equals this. For that, we're interested in x less than 2. Let's plot the graph of y is equal to minus x plus 2. You'll agree with me that the y-intercept is going to be at 2 somewhere here. And x-intercept, when y is 0, x will be 2 there. So basically, we are saying that this is the story. If you allow me to move straight up, down, that is how our graph looks in simple terms. So now, look at our integral. This is our integral. The integral from 0 up to 2 of the absolute value of x minus 2 dx. It's basically this area here. This area here. Remember, I told you that that's 2, but we're not interested in that. We're interested in just values of x from 0 up to 2. So we're not so much focusing on this, the right side. We're focusing only on the shaded area. That means our function, the function we're going to deal with is this one. There are 2 ways in which you can answer that area, find that area. Simply finding area of this right angle triangle here. You agree with me that area of a triangle equals half base times height. What is our base? Where our base is 2. What is our height? Where our height is 2. Base, height. This simplifies to, if you like, 2 square units. But since we're dealing with differential calculus, let's see if we integrate this from 0 up to 2. Let's see if it gives us 2 square units as follows. So we're going to say, therefore, our integral from 0 up to 2 of the absolute value of x minus 2 dx, this is just equal to the integral from 0 up to 2 of minus x, remember, plus 2, and then dx. Now, integrating minus x, the answer is minus x over 2, x squared over 2, remember, plus the integral of 2, where is 2x. What are our limits of integration? Limits of integration from 0 up to 2. Punching in 2 here and there, you agree with me that the answer is going to be minus 2 squared over 2 plus 2 times 2. If you punch in 0 there and there, the answer will be 0. What does this simplify to? Well, if you check, it actually simplifies to, this is going to be minus 2 plus 4. The answer is 2. And because we're dealing with area, it has to be square units, basically. This is our solution. Or you can just leave it as 2. We know we're dealing with area here. So this is the solution to the second integral. Now, if someone did not just, someone just went with x minus 2 as the square root of that, you would not end up with the correct solution here, because you would be focusing on that function there. Remember, that's the line y equals x minus 2. You would be focusing on that line only. And from 0 up to 2, you would be finding the area which is going to be the negative value, negative area. Of course, this under this cross sign, under the x-axis, you'd be finding that shaded part. If I were to shade this part here, that would be the area you're finding, and that would be the incorrect solution. And I want you to try this one out, because basically what I'm trying to say here is, let me take this page. If you took, suppose you took x minus 2 and you said we're integrating from 0 up to 2 dx, this would be x squared over 2 minus 2x. Limits of integration 0 up to 2, putting in 2 there, it will be 2 squared over 2 minus 4. 2 there, 2 times 2 is 4. This is 2 minus 4, and the answer is what? Minus, which is not the correct answer. Of course, if you substitute 0 here, to be minus 0, and it gives you that, which is incorrect. And the correct solution is when we consider the positive square root there in terms of absolute value sign. All right, so that is the solution to our second integral. Very tricky, I must say. This again emphasizes the fact that in differential calculus, especially integration, when you're given a question, don't rush to try and answer it. Think first, and then get back to looking at different approaches or techniques that you would apply. Right, let's look at this one here. Now, this is a horrible integral, I must say. And I challenge you to look at this one. Attempt it before you come here and try and look at the solution for number 3. You will actually see that this one is one of those MIT integrals. Very, very tricky. But where do we start from? Well, looking at the numerator, you see there's a minus 3 and the minus 2 there. So I can take the minus out. That would be the starting point. So here is my approach. And I'm going to say something very, very serious here. You better take note of. Let me capture this integral number 3. So we're talking about the integral of minus 3 minus 2 sine x all over 2 plus 3 sine x all squared, and then we have dx. Like I said, first step, factorize the numerator. So this is integral of minus, if you like, minus 1, but I'm just going to put minus 3 plus 2 sine x. And then I have in the denominator 2 plus 3 sine x all squared dx. Now, let me just clean up a little bit here. Right, now, what is the approach? I'm going to take the minus out. Minus 1 or minus. So this is going to be minus the integral of 3 plus 2 sine x all over 2 plus 3 sine x all squared dx. Right, step number 1. Now, there is if you remember in the lower classes, when you're looking at algebra, there's something here that we need to apply, the simple basic principle that if I have a fraction, for example 3 over 5, if I divide the numerator by 2 and the denominator by 2, I don't change this fraction, it remains the same. What are you saying? This is what I'm saying. This is exactly the same as 3. If I say divide by 2, 5 divided by 2, it's the same expression. That, let's work on this and see if it gives us this. What is the numerator? The numerator is 3 over 2. We're dividing by denominator 5 over 2. These are two fractions that we must work on. So 3 over 2, and we're saying divided by 5 over 2. Remember, 3 over 2 times, this has to be reciprocated, 2 over 5. These cancel. Where are you at? 3 over 5. You end up at the same fraction. This may look very simple, but this is what we're applying here. So basically what I'm saying is, there's a trick. Whenever you see that the constant term there is the coefficient of sign in the denominator. So I'm looking at the numerator. The constant term is the coefficient of sign in the denominator. And the constant term in, the coefficient of sign in the numerator is a constant term in the denominator. You can see these numbers are swapped. When that happens, you divide in the numerator by the square of cosine and the denominator by the square of cosine. It always works. So that's the trick that I was talking about. Watch what happens. The integral of 3 plus 2 sine x, this divided by cos squared x, and the assumption is cos squared x is not equal to 0. We're dividing this by 2 plus 3 sine x all squared divided by cosine squared of x dx. Now, because the two expressions are quite big, I'm going to work on the numerator separately, denominator separately, and then bring them back in. So basically what I'm saying is, let's just simplify a little bit the numerator, and I'm saying here, if I may put it here, and I'm saying numerator. The numerator is, if you like, 3 plus 2 sine x all over cos squared x. This simplifies to, if you check term-wise division, it will be 3 over cos squared x plus, there's a plus sign there, 2 sine x over cos squared x. What does that simplify to? Let's come to page number 6. That expression simplifies to, I move down a little bit, right? That expression simplifies to, moving down this way, you'll agree with me that it will be actually equal to 3 over cos squared x is actually 3 times 1 over cos squared x. And then I have plus this part here, you'll agree with me that it's 2 times sine x over cos x times 1 over cos x. What is this? Well, this is 3 sec squared x plus, this is sec tan, so it's 2 sec x tan x. That's the numerator. Now let's work on the denominator. Denominator, how does it look? Well, the denominator is this part here. So it is 2 plus 3 sine of x, and it's all squared divided by cos all squared of x. This simplifies to, if you like, let me use big brackets, 2 plus 3 sine x all over cos of x, and I square the whole of it, because the numerator is squared, the denominator is also squared. And I'm going to apply term-wise division inside there. I'm going to get 2 over cos x plus 3 sine x over cos x all squared. This simplifies to, this is actually 2 sec x plus this, if you agree, it will be 3 tan x, but it has to be all squared. Now I'm going to take this expression and this expression into the integral. Maybe at this point, let me just go straight there. Going into the integral now. Which integral are we talking about? This part here. I'm replacing that and that by this expression here, this expression and that expression there. Remember, there's a minus outside our integral sign there. There's a minus. So basically, I'm saying, let me go to page number 7. I'm saying what we have now is minus the integral of, in the numerator, I'm going to have this expression. So I have 3 sec squared of x plus 2 sec x tan x. In the denominator, I have this expression here. This is what I have. Remember, I told you in the numerator we have this, in the denominator we have that. So it's 2 sec of x plus 3 tan x. And we are saying all this is squared dx. This is what we have. Now there's something interesting here now. Notice that now if I say let u be equal to the denominator, which is 2 sec x plus 3 tan x, and I differentiate both sides, I'm going to have du on the left is equal to, what's the derivative of secant? It is actually sec tan. So this is 2 sec of x tan x plus derivative of tangent. Remember, 3 is a constant. This is 3 sec squared x, derivative of tangent is sec squared. Now notice I have to say here dx. This expression here, if you check, is actually that expression there if I put this in brackets. So basically, let me rewrite this. So I'm saying now we have minus the integral of, check this, 3 sec squared x plus 2 sec of x tan of x dx all over, we have 2 sec of x plus, and I'm replacing that. I have to replace that now by this expression. No, I'm gonna skip this one because remember the numerator, our numerator is this one there, which is basically this, and I'm gonna keep that one the way it is. 2 sec x plus 3 tan x, and we're saying squared. And now notice I must perform substitution now. What is this one now? It's gonna be u squared. The numerator is gonna be du. You can clearly see there the integral of du over u squared. Amazing. So this is basically the minus the integral of u to the power minus 2 du. I'm just gonna use power rule here now. The inverse operation of differentiation is integration. Taking us to page 8. Basically what I'm saying now is, hopefully you can see what I'm writing. Oh yeah, you can. So now I'm saying this, that integral is just equal to, watch this, I'm going to say minus, and we have u power minus 2, I add 1, and I check that result, minus 2 plus 1, I divide. And I must say plus c because we're dealing with an indefinite integral here. Simplifying this, we have minus u to the power minus 1 all over minus 1 plus c. The minuses cancel, so I have u power minus 1 plus c, which basically is 1 over u plus c. What is u? Let's go back. U is this expression here. So my solution then, this is going to be equal to 1 over, remember, 2 sec x plus 3 tan x. So 2 sec x plus 3 tan x, and then I'm saying plus c. This is the final solution to this integral. Now, you'll agree with me that maybe if I may use a football analogy, there is a point where they talk about moment of brilliance. And here, right here, this is the moment of brilliance, just to see that when the numbers are swapped like this and you're dealing with sign here, dividing by cos squared, and especially if you have a square in the denominator there, that expression is squared. Even if without a square, as long as you have that expression in the denominator, if you swap, of course, with a square, it works better because cosine that you divide here is squared. Turns out that what you get is this integral here. What you get is this part, because the numerator now, remember, has been replaced by these two expressions. You say, where did we get that? Well, we got them from here. The numerator simplified to that which was giving us, I think I must talk about page 6 here, was giving us that. And then we had to work on, I hope you can see that, yeah. Let me put this one straight. Then we had to work on the denominator, which was this, simplifying, and noticing that if you differentiate this, it actually gives you that. Derivative of sec is sec tan, so it will be 2 sec tan, which is this part, plus there. Derivative of tangent is sec squared, so it's 3 sec squared, which is this expression. And therefore, the entire integral works out very smartly and nicely like that, coming up with our final solution on page 8. Our final solution, I think, is on page 8 here. There it is, as our final solution. Right. Let's move on to our final integral in this video. There is our final integral. Integral number 4, we are saying the integral of 1 over x plus x cubed dx. How do you deal with this? Well, for starters, you can clearly see that the denominator there is a common factor there. And the common factor is actually x. So let's start from there. We factorize the denominator. So integral number 4, it's the integral of 1 all over x plus x cubed dx. Like I said, this is the integral of 1 over x 1 plus x squared, and then we have dx. At this stage, when you look at that expression there, we can only run to partial fractions, and therefore we're going to say 1 over, so I'm talking about partial fractions now, partial fraction decomposition. So what are we saying? We're saying 1 over x, 1 plus x squared. This can be written as capital A, where a is a constant, over x plus. Remember, this part is quadratic, so we have to say the expression in the numerator must be a linear expression in terms of x. So bx plus c all over 1 plus x squared. Our job is to find the values of a, b, and c. How do we do it? Well, here's how we do it. The common denominator there is this expression, the same one, by the way, like this. We take this into that, the answer is this expression, multiply by a, so it will be a times 1 plus x squared plus this expression into the denominator, the answer is x, times the numerator, x times bx plus c. Let's expand, simplify the numerator. What we have is a plus ax squared plus bx, a times a times 1 is a times ax squared is ax squared, and then x times bx, the answer is bx squared, x times c is cx, right, all over x 1 plus x squared. Where are we coming from? Remember, we're coming from 1 over x, open brackets, 1 plus x squared, 1 over x, open brackets, 1 plus x squared. Now what do we say? If two fractions are such that the denominators are equal, the numerators must be equal. Therefore, our conclusion then is, watch how I'm going to rewrite 1. 1 can be written as 0x squared plus 0x plus 1. Of course, we know that that is 0 basically. But I'm doing this because in the numerator on the right-hand side, I am going to take these terms containing x squared. It's going to be a plus b if you factorize, and we have x squared outside. And the term containing x alone is cx, and then our constant term is a. Why am I doing this? Because now I can say coefficient equals coefficient, coefficient equals coefficient, and constant term equals constant term. So basically now I'm saying a plus b equals 0, a plus b equals 0, and I'm also saying c equals 0, remember, and then I'm saying and a equals 1. Now clearly you can see if a equals 1 here, b will be equal to minus 1. Because you take 1, put it here, and so for b is going to be equal to minus 1. Now we take 1, 2, 3 values into that part and then rewrite the integral as follows. So now what we have is the following. We are saying, therefore, our integral, which is 1 over x, 1 plus x squared dx, simplifies to the integral of 1 over x. Remember, a equals 1, so you put 1 there, 1 over x, and b equals minus 1, c 0. So what we have now is we're going to say plus minus 1 all over 1 plus x squared. All this is supposed to be integrated with respect to x. So we're changing that into this expression here, put there, and then we perform integration. It's easier. Let me put this aside now. Let's distribute the integral sign and that. So this is going to be equal to the integral of 1 over x dx. If you like, this is going to be minus the integral of 1 over 1 plus x squared dx. Right. Now, in the previous video, I did explain, a couple of videos, I did explain that this is actually tan inverse of x. And we know the integral of 1 over x is natural log of x. So this is basically the natural log of x, and then we're saying minus tan inverse of x, and of course plus c, because we're dealing with an indefinite integral. So basically that's what we're saying. Well, if you want me to explain how this is equal to this, drop some comments in the comment box below, and then I'll attend to it. But basically this is what we're saying. Our integral, which integral are we dealing with? This one here, which when you factorize the denominator looks exactly like that. simplifies to that. So that's our final solution in integral number 4. So these are the 4 integrals that I had. I hope you enjoyed the techniques of integration. Is a very big thing as far as differential calculus is concerned, and obviously integral calculus. All right, I am going to stop here. We'll see you in the next one.